Section 9.3, applications and probability. The first application that we're going to take a look at is the application of odds. All right, so odds. If you have P of A and it's the probability of an event A, and P of A bar being the probability that the event A doesn't happen, then if you have the odds in favor, and I put the parenthesis in favor because it's not always written that way, it usually just says the odds. The odds of event A are the probability of event A divided by the probability of not event A, or the probability of event A over 1 minus the probability of event A. And I challenge you to say that 3 times fast. 3 is all it would take, I think. And then we've got the odds against something happening, and all you see is the fractions flipped upside down. That's all you see. It's the only difference. So jot those pieces down. And then tell me, where have you heard the word odds used? Vegas. Hunger Games. You know, before the Hunger Games, nobody ever had this as an example, and now it's every time example. Okay, so Vegas, you hear it with Hunger Games. Where else?
That's odd.
Oh, I mean in a mathematical sense, but good point, Alyssa. The lottery, what was that? The game, what are the odds? Okay. Another one that, somebody said it. Who said what? Oh, sorry, something different. Another place that you will hear it, and this is probably good that you wouldn't know this, I guess, but is you in particular hear the word odds used in racetracks, like horse races. The odds of a certain horse winning something. So odds have to do with probability. Obviously, they're related to probability. The values of probability are all over these definitions, right? Okay, so we're going to do an example. Just jump right in with an example so you can see where these pieces are coming into play from our example. All right, so we are not doing horse racing or Hunger Games or anything like that. We're doing marbles. We have 8 marbles. There are 5 red and 3 white, and we're going to pick one at random. So the first question is something we've already done. What is the probability that we're going to choose a red marble? 5 out of, what was it? 8. Good. Okay, so probability is writing this as the desired outcomes out of all outcomes, right? Odds is also a comparison, but it's a comparison between desired outcomes and not desired outcomes. So when we're writing odds, we write the 5 still on top, but on the bottom we write the number of outcomes that are not what we want, and that's 3 in this case. So these are ratios, they're comparisons, and you've actually seen them done before when we were looking in chapter 6 at fractions and proportions. The place that we saw them used was when we were talking about ways of writing a ratio, a part-to-whole ratio and a part-to-part ratio. Do you guys remember that one? The specific example that's coming to mind for me is the one where we were comparing the number of girls in the class to the total number of kids in the class, and the number of girls in the class to the number of boys in the class. All right, so the comparison being made is a comparison to something else that's not the desired outcome. Right? So this is a 5 to 3. Let me do another example with you. This one's worded a little bit differently, and it doesn't have marbles. It has rain. All right, so this is the probability of rain for the day is 60% chance. And this wants to know that the odds against it raining. So the first thing we want to take a look at is what is the probability that it doesn't rain?
40.
Right. 40%. And let me actually write that as a probability, and I'll write it as 0.4. And then the probability that it rains, of course, is what? 0.6. Okay, so these are the 2 pieces of information that I need to know to actually get the probability or the odds against it doing something. And the odds against it doing something mean that I want the ways that it, in this case, doesn't happen on top, i.e. the ways it doesn't rain, compared to on bottom the probability or the ways that it would rain. So what would I get for the odds, and it's odds against on this one? It raining. What would go on top? That would be the 0.4, the 40% either way. And then on bottom? my 0.6. Then I need to reduce that. So multiply by a power of 10 if you'd like, just so that we don't end up with decimals. I have 4 over 6, but then what would I do with the 4 and the 6? I reduce, and I would divide by 2, so I have actually 2 to 3. You will also see this written just like with other ratios where we have the colon between them like this, 2 to 3 odds. So it's both fractional notation just like with ratios and ratio notation where they're side by side with the semicolon between them, or the colon between them, excuse me.
I like this.
So you like this?
Yes.
You good so far?
Yes.
Excellent. I'm so glad. All right, a little bit more with odds. So we basically talked about how to take probability and turn it into odds. That's what the definition is describing, right? So the next theorem actually says, but what if I wanted to go the other direction? What if I were given information about odds and I wanted to find out what the probability of something is that's happening? So if you have the odds of an event happening, or m to n, then the probability of the event happening is m divided by m plus n. And this should just scream boys and girls in a classroom, because this is exactly what we did when we did this example before. We had a ratio of boys to girls of like 2 to 3, and we said, how do we get the ratio of boys to the whole class? And we said, oh, well, we just need to add the 2 and the 3 as the denominator. That's all we do. And that's exactly what this is saying. Now, the part that's not quite the same, or that we haven't exactly seen written this way, is this odds against business. So if the odds against the event happening are m to n, then the probability of the event happening would be n on top, because that's the way that it happens as a desired outcome, and then still the m plus n on the bottom. Okay? So we're going to do an example where we're going to draw a tree diagram, because you guys are really good at them now. So you're going to need the bottom of that page, because you need to draw your diagram there. Okay? So I need us to draw a tree diagram for a 3-child family. Not 4, but just 3. Okay? So 3 branches. So we're going to start out by having child number 1, and they are either a boy or a girl. And then we're going to have child number 2. And then child number 3. And what number is on every branch? 1/2, yeah. And if I multiplied every branch all the way out, what would every branch be? 1 what? 1/8, right? 2 times 2 times 2 on bottom is 8. Okay. So every branch, just to think about it this way, is equally likely. That's actually what I'm kind of wanting to make sure we understand. 1/8 on all of them. So this goes all the way down. All right, first question says, what are the odds of having all the same gender of children? So using this diagram, what pieces are the desired outcomes? All boys or all girls? I was about to say so they could share clothes, but if it's boys, they're going to ruin the clothes, so it's not going to work out. And if girls, they may not want to share, so I'm not sure it's going to help anyway. All right, so the odds of having all the same gender, these are the 2 things that are the desired outcome, right? So my odds would be a 2, the ways I get what I want, compared to 6, the ways that I don't get that desired outcome. Okay, 2 compared to 6. And we'll reduce just like we would have before. So this reduces to 1/3. Yeah. This is the odds are 1 to 3. There's a 1 to 3 odds that I end up having all the same gender of children. What is different about question B? It's the odds against. So if I've already found the odds of having this happen, what do? I can just flip it. Yeah, it's that simple. So the odds against will be 3 to 1. And we're not going to reduce 3 to 1 to say 3 because that doesn't work within the context of what we're talking about. So we really are going to leave it 3 over 1. Okay? And all I had to do was to flip it upside down. There's 3 ways to not get what I want. That's the odds against getting. And there's still one way, I mean, when it's reduced, of actually having what I want, so to speak. Okay, any questions about that one? Now, the only reason this worked is because all those probabilities were the same. Do you guys recognize that? What if they'd been different? Well, if they'd been different, I would actually have had to use probabilities. Like I would have had to add up all the probabilities that satisfy whatever, and maybe it ends up being 0.3 on top, and then I'd have 0.7 on bottom, right? Like instead of getting just the whole number 2 right here and counting the number of ways that happen, I would have actually had to figure out what the probability individually, total combined, of my desired outcome was, and do it with probabilities. So that ends up being a little bit different. All right, the other application in this section that we're going to look at is expected value, and this is a fun one. So first of all, let me just say expected value has to do with something that has numerical outcomes. Okay, so our boy-girl examples don't even make any sense right now. Okay, we can't talk about families of kids now. We have to talk about something where it has numerical outcomes. So we're going to see examples of games where you actually earn money, right? And in particular, or sometimes I'll do an example where it's a carnival and you're earning tickets, but it's still using some kind of a numerical value of something you're getting for a result of doing something. So if the outcomes of an experiment are A1 through AN, with probabilities P1 through Pn, then the expected value is A1 times P1 plus A2 times P2 all the way down until we get to the very last probability and outcome. And if a game is considered fair, then it means that the expected value is 0. Now, contextually, what that means is if you played the game enough times, you would have an equally likely chance of having no money gained as you, I mean, your expected outcome would be that you didn't lose or gain any money by doing it. Okay, so this idea of a fair game is not usually what anybody operates under the assumption of. I mean, if they did, the casino wouldn't have the nice building. Right? I mean, just think about it logically. They can't have fair games or they're not going to make any money. Right? So this idea of a fair game is not something that you actually see happen in reality. So let's take a look at some examples so you can see how it works. We're going to do a roulette wheel. Who's seen a roulette wheel? Oh, about half of you. Okay. A roulette wheel looks like a giant spinner. Okay? So just imagine the spinners that we've seen so far. And it's split into how many regions does this say? 38, actually. So there's 36 numbers, 1 through 36, but then there's also a 0 and a double 0. So there's 38 different little slices of the spinner. That's what you've got. One way to bet is to bet on a single number. You can also bet on red or black or white or green, whatever the colors are in the square or on the slices themselves. But we're just going to talk about betting on a single number. And that's not exactly quite true. I'm going to change that in just a minute. But we're going to talk about how we can bet. If you actually have your ball land in the sliver of a piece, you know, that you said it was going to land in, they give you your original chip back that you bet, and they also give you 35 more chips. So, like, the return on your money is pretty good. I mean, like, right? You risked 1 and you got 35. So that's part of the draw of this particular game is that there's this really high payout if you win. Okay? So the first question that we're going to ask is, what in the world is the probability that you will, in fact, land on any particular space? So what is the probability that you will land on 0, 0? 1 out of 38. And the probability that you will land on 0? 1 out of 38. And what would be, we're going to use this in a minute, the probability that you land on either of these? Either one or both. I mean, you can't land on both. That's not a possibility. It would be a 2 out of 38, right? So we're going to think about that in a minute, use that little fact. They didn't ask us this question, but we're going to use that fact in a minute. Okay, so it's got this high payout, but you also have this very small chance, right? 1 out of 38, that's pretty small. There's 37 ways that it doesn't work out for you. Okay? So we're going to calculate an expected value. This is a little bit of a complicated one. Whoops. Okay. I have a father-in-law. He's a wonderful guy. He's not mathematically savvy when it comes to gambling. He's not like somebody who goes and wastes all his money, but this is exactly what he does. Guaranteed exactly what he does. When my father-in-law passes a roulette wheel, if he sees that it has not landed on the 0, 0 or the 0, Okay, either of those two places, which are, I believe they're the green slices in a roulette wheel. If he sees that it hasn't landed on that in recent history, he will bet on it. So what do I mean by recent history? Well, they have these like a marker board, if you will, a marquee board next to it, and it tells you the last, 10 or so rolls or something that they've had, and it tells you what it's landed on. So he looks in this list, and he sees it's not landed on 0 or 00 anytime recently. He'll make a bet. Can you see my eyes? Okay. He'll make a bet. And so we're going to give the probability of how this works out. And he will bet on both numbers, actually. He'll put money down on both of those numbers. Okay, so if he bets one chip on each number, and a chip is worth $10, what is the expected value of his bet? All right? So there's two things that could happen. What are they? Wins or loses. I mean, those are the only two possibilities here. Sometimes you'll win more if you bet in certain ways with certain games. I'm thinking about like the movies you see about like craps and stuff like that where they throw the dice and whatever, and there's different ways you can bet on that. But in this one, this is very simple. He's either going to win or he's going to lose. One of the two things. I am not, Andrew. What? I watch lots of movies. How's that? All right. So we've got, I'm sorry, I meant to put E there. The expected value. So the first question is, what is the probability that he wins? And if he wins, how much? Okay, and then we want to know the probability that he loses. And again, how much? And that's really all expected value is. It's making a mathematical assessment of the likelihood that you win versus you lose. All right, so let's see what happens. If he wins, and this is not quite so straightforward because I've put a lot of numbers in here. If he wins, how many chips does he win? 35. He wins 35 chips, correct? Okay. But how many chips did he pay to play? He paid 2, and they're going to give him back one of them, the one that he won with, right? So what is the net change in his chip stack? Not dollars. I just mean the number of chips. It's 34. Okay? He paid 2, and they gave him back 36, right? The 35 he won plus the one chip that he bet that it was the winning chip. Are you guys with me? Okay, so he paid 2. That's minus 2. They gave him back 36, the 35 plus the winning chip that was already on the number that he actually won on. So he actually wins 34 chips, right? But they're each worth $10, which means he had a value of $340. All right? So the how much part is $340. Every time you do these problems, you have to keep in mind, but how much did it cost me to play? Okay, so you roll the dice, but it cost you $5 to play. You got to take that 5 out. Okay, you didn't really win that. That was your risk. Okay? All right, what is the probability that he wins? That was 2 out of 38, which we could reduce if we wanted to. But yeah, it was the 2 out of 38 that we looked at on the previous slide, right? Okay. Now, what is the probability he loses? 36 out of 38. If he loses, what is the change in his chip stack? Two chips, right? He has 2 fewer chips than he had before. Worth how much each? $10. So the net change in his wallet is $20, and it's negative 20. It's a negative. He is out $20 that he previously had. Okay, there's going to be negative numbers in here because you're paying to play things. All right, we're going to multiply this out, add things together and whatever, and I want us to find out, and remember, this is going to be a money amount, so it's appropriate to have 2 decimal places. Change. We need 2 decimal places in our answer, and it is a dollar amount, and we could get a negative, right? In fact, most of the time we will get a negative when we're talking about gambling. That's kind of the point. Okay, what do we get? Is that what we have? I have something different written down, but I could totally be just have made a mistake when I calculated it.
1789.
Oh, we got 2 answers now. Neither of them match mine. Okay. Let's try another one. with it, Alyssa. What's it say? Okay, that's what I have written down. So I'm going to think that's correct since you got that one too. Negative $1.05. That's what that says, right? So what does this mean over time? Well, it means if I played the game a whole bunch of times, sometimes I win, sometimes I lose. But the net result is that every single time the average loss would be $1.05. And that's why the casino can stay open, is because the average gain to them is $1.05 on the game. Make sense? Okay, so this is expected value. It's over the course of time with wins and losses playing this, again, Bernoulli's equation, right? You know, like hundreds of thousands of times what happens. That's what you're looking at for this scenario. All right, another one. Have you guys seen Deal or No Deal? Yes. Okay, good. Deal or No Deal. A contestant is down to 2 cases with equal probability of being chosen. The cases have $250,000 in them and $10 in them.
Oh, God.
Oh, what a killer. If you were the banker and you want to give a reasonable offer to the contestant, not too lucrative, you know, so like you're still the banker, right? What deal would you offer and why? This is an expected value question. This is how they made the decisions when they were making the show on their offers. So what we would do is we have 2 possibilities for our contestant. They're both wins, right? I mean, the contestant wins in both situations. I'm not really sure you're going to say that they really win if they win $10. But, I mean, technically, you know, they win. So what is the likelihood or the probability, well, it's right here, that they win big? And then the amount, right, that they win. Those are multiplied together. Plus, and then we have, in this case, the other option, which is the probability that they win small. And then we have the amount that they win if they win small. All right, so what's the probability they win big? 1/2. And if they win big, how much do they win? $250,000. Good job. What is the probability they win small? 1/2. And the amount they win? $10. So grab your calculator. Tell me what you get. Again, this is a money amount, so I'm going to put a dollar sign. Decimals are appropriate with 2 decimal places if we need them. What'd you get, Kayla? And of course, if you've watched the show, you know they don't offer in $5 to anything. This is what I need to know in order to make my decision about what to offer. Now, it's not actually the answer to the question, but it's what's going to help me make my answer to my question. So it says, if you want to give a reasonable offer to the contestant, not too lucrative, what deal would you offer and why? So what kind of a number are you looking for? Something less than this, but close, right? If it's not close, the person's probably, well, they might still take it because this is $250 or $100, I mean, or 10. But the idea is the number that they're going to offer is going to be pretty close to that, right? So what offer would we make? So we're going to make an offer that's close to 125. Maybe. This is where you get to sort of make your decision. So the answer, generally speaking, just is it needs to be close to $125,000. And the reason, I'm not going to keep writing because my pen's not writing very well today, but the reason is because that's the expected value. I mean, you know, the justification, the work that you just did is, in fact, the reason. The reason is because that's the average expectation of this game. You know, so if this time this contestant plays this game and they win $250,000, next time the expectation might be that they don't win the $250,000. So it balances itself out, right? So we're looking for the balancing, the point, that scale point where it evens itself out. And that's what we're looking for when we're making that deal as the banker. Okay, any questions on this one? Okay, we have one more. Lottery. Actually, I'm pretty sure when we're all said and done, I'm going to teach you not to gamble. That's my goal. All right. In a given lottery, we know that the odds of winning the lottery are 55 million to 1. So they're like giving us that information on this particular lottery. That's what they're saying, okay? Those are our odds. If the odds are 55 million to 1, what's the probability that you're going to win? 1 out of what?
55 million and 1.
Oh, yeah. So this is a little bit tricky because the number is given to us with the word million after it. So this would actually be 55,000,001. Don't get carried away and tell me 56 million. I have this shirt. I have a couple shirts like this where it says, I think it says 147 million on one side. And then on the back it says -1. It's an adoption shirt, 147 million minus 1. And this is exactly what my son has done before, my little one, who said, well, it may actually have been my daughter Abby. It probably was because it's been a couple years ago. And she looked at it and she says, that's 146 million. And I said, no, we didn't adopt 1 million children, right? It's not 146 million. It's still 147 million minus 1, not minus 1 million. Okay, so we have to be careful here. Same thing. It's 55,000,001 on the bottom. Okay, you guys good? Okay. If the grand prize is 14 million and a ticket costs $5, is the game fair? Okay, so what did it mean for it to be fair? We had that defined before. Expected value is 0. So if we want to know if a game is fair, we have to calculate the expected value. So that's what we're going to do. And just like with the other games that we've looked at today, there's 2 possibilities really in this one. And some games have more possibilities than that. And you'll encounter some of those in your homework where you'll multiply the probability of, kind of like we did, winning big, winning small, maybe winning nothing at all. I mean, you might have 3 or 4 probabilities. But this one, there's just 2 things that can happen. You either win or you don't. Okay? So we've got the probability that we win, and it's multiplied by the amount. How much do we get if that happens? Plus the probability that we lose. And again, the amount. You know, how did our net worth, if you will, the amount that's in our pocketbook change? All right, so what is the probability that you win? 1 out of 55 million and 1. You're not supposed to say and there, but it still feels so awkward, right? 55 million 1. How much do you win?
13,999,995.
Okay, say it louder.
14,999,995.
Close. I don't think you wanted 14 at the beginning. You went 13, right?
Yes.
Okay, so Andrew, why is it 13,999,995? Because you paid $5 to pay the game. You guys with me? You have to remember, you paid money to play. That's part of the change in money here, is that you paid 5, they gave you back 14 million. I know you're probably thinking, so what? I mean, like, really? 14 million, 5? Okay. But it matters in terms of the calculation. Oops, I didn't mean a 14 here. So we have 13,999,995. Fabulous. What is the probability you lose? 55 million. You're in good company if you lose, because pretty much everybody lost, right? Out of 55 million and 1. And what is the amount? -5. Okay, now here's a cool thing to notice. These are fractions, right? And they're fractions that have the same denominator, correct? So really we could just add this 13,999,955 to this number multiplied by 5, the 55 million times -5, right? And then we can write that as and then we can divide just one time instead of working with the funny decimals for so long. So my suggestion is to take 55 million and multiply by -5, and then add the 13 million and the almost 14 million to that. And once you hit that value, hit enter, and then divide by the 55 million 1. Get a value? I think it's negative still, right?
-475.
-475?
Yep.
Andrew says that's that what you got, Selena?
Yeah.
Yep, then you didn't get it wrong. You got it right. Yeah, it's -475. So on average, you play this game enough, right? Sometimes you win, sometimes you lose. You're never going to win, but pretend. Sometimes you win, sometimes you lose. But on average, you lose almost the whole $5 every time, right?
Yeah.
I mean, you paid $5, and you're losing the $4.75 on average, right? Every time. Okay. All right, so let's actually look at what happens to the way that this works out. As with many state lotteries. Sorry, yes, what was that?
So it isn't fair?
Correct, thank you. I didn't actually say that. Yeah, the answer is no. It's not fair. And why is it not fair?
It doesn't equal 0.
Yeah, it's because it doesn't equal 0. It's not because you're upset that you lost. That's not the not fair reason that we're going for here. Okay, sorry about that. What's that?
So if you do win the 14 million, it is fair?
You probably feel like it is, don't you? Yeah. Amy?
So, would the negative $5, would that be added to the negative 475 for a total loss?
No, it wouldn't. This is the total outcome of your expectation.
Okay.
Yeah, it includes the negative 5. All right, part C. As with many state lotteries, the proceeds are often said to benefit education. Under these conditions, if all proceeds benefit education and 1 million tickets are sold, what is the expected value from the lottery sales? So the consumer loses 475, which means that education gains it, right? Then you multiply by 1 million. Very good, Lauren. So we're going to take that 475. It's not negative now because we're doing it from the perspective of the person who earned the money, who received it, right? And we're going to multiply that, like Lauren said, by 1 million. Okay, so we're going to multiply, and what are we going to get? Amount of money. 4,750,000. That sounds pretty good, right? Education gets it. Because people were not educated, I guess. A little bit of a problem with that, but all right, it might be a little counterproductive. All right, so let's take a look at the reality, though. Part D says, what are the actual possibilities of amounts applied toward education? This 4 million number is an expectation over the long haul, right? So in a given lottery cycle, when the lottery happens, if 1 million tickets are sold, this is not what's going to happen on a given specific example, right? This is like you in the roulette wheel. You're not going to win, whatever that number was. What did we have? 105, right? I mean, you're not going to lose 105. You're either going to lose 10 or 20 if you've bet this way, or you're going to gain the 340. Those are the two possibilities, lose 20 or gain 340. So that's kind of the same thing that's going on here. It's not 4.75 million. That's not what this is. What would we do to figure out what the real possible outcomes are? Well, what are the two things that can happen when the lottery's played? Somebody wins, or nobody wins. And that happens all the time, right? That's when you see the jackpots go up and things like that on the billboards. So there's two possibilities, is that we have a winner. In fact, I'm going to start with the no winner situation. If there is no winner, and people have paid $5 to play, right? And 1 million tickets are sold, what does this give me?
5 million.
Yeah, 5 million. So this is 5 times 1 million. What if there is a winner?
You gotta pay 'em.
You do. You have to pay them. How much?
14 million.
14 million. Do you see a problem?
Yeah.
What's the problem?
More than you're getting in.
That's exactly right. We collected 5 million. And we're paying out 14 million. And that's a negative number, last I checked. Negative 9 million.
It's crazy.
Now, the negative 9 million is less likely to happen, right? We get that. But it's still a possibility, right? So we either hope for somebody to win, which does not benefit education, right?
Yeah.
Or we hope everybody loses.
Still doesn't benefit education.
Yeah, I mean, like, this is not a good scenario. Agreed? It's not so good.
But wait, what if